now I would like to introduce our very first speaker for today, and that is Tizian Serichova-Dragomir, who will help us understand variants in the TypeScript type system in his presentation. Tizian is an engineer at Bloomberg working on TypeScript and JavaScript infrastructure. He is also a TypeScript compiler contributor, as well as being one of the top answerers with regard to TypeScript on Stack Overflow. And of course, as you can imagine, he's a huge fan of TypeScript, and he will try to convince you that you should be one too. So now, without any further delay, I bring you Tizian. Hello, Tizian.
Hello, everybody.
Once you're ready to share your screen, I think we can...
Yeah, I'm getting ready to share.
And here we have it. Okay, Tizian, the stage is yours.
Thank you very much. So, hello, everybody. We're going to talk about variants in the TypeScript type system today. So we will first of all talk about how variants, what variance means, and we're going to relate this to a generic type. We're going to talk a little bit about how TypeScript actually uses variants internally and how that actually surfaces inside TypeScript. And we should also see exactly why should actually care about this. And I hope that I will manage to convince you that variance is not just some arcane type theory thing, and it's actually something with real world impact that you should care about. So we're going to start off with a little bit of a tangent. We're going to ask a simple question. How can we tell if something is a base type of another type? So in other languages, this might be simple. In C#, for example, or in other nominal type languages, you might just look at the base type and you would find exactly what the base type of a class is. In TypeScript, it's a little bit more complicated since TypeScript is structurally typed. So a type can have a multitude of base types. So how can we tell if something is a base type? Well, the proxy we're going to use today is assignability. Now, assignability is not a perfect proxy for the subtyping relationship. There is something called excess property checks that is not part of subtyping, but it's generally a pretty good proxy, and we're going to use it in this presentation. We are also going to use conditional. We could have also used conditional types, but the syntax there is a bit more wonky, and I think people are more comfortable with assignability. So when is something a base type? Well, if we have a subtype of something and we try to assign it to a reference that is typed as a base type, that assignment should succeed. So what does this have to do with variance? Well, at its core, variance is a way to gain insight into a subtyping relationship. Basically, if we have a generic type, let's call it list, and this type has a type parameter, and we instantiate this type with two other types that we know are related, the question becomes: is list of those two types related in any way? For example, if we have a dog, which is a subtype of animal, and we instantiate list with animal and list with dog, are those two types related in any way? And the answer is that they can be. And the ways that they're related gives us the variance of that type parameter. For example, we could have the arrow of inheritance pointing in the same direction for these two instantiations. So if we have dog, which is a subtype of animal, then list of dog is going to be a subtype of list of animal. And this, of course, also means the related assignability. Namely, we can assign a list of dog to anywhere a list of animal is expected, but not the other way around. Contravariance, contra meaning opposite, right? The arrow of inheritance points in the opposite direction. That means if we have our same example with dog is a subtype of animal, if we instantiate list and list is contravariant, then we actually get the fact that list of animal is a subtype of list of dog. And also the assignability is reversed. Right now we can assign a list of animal to anywhere a list of dog is expected, but not the other way around. The third type of variance is bivariance, right? namely the arrow of inheritance points in both directions. This means that both list of animal is a subtype of list of dog, and list of dog is a subtype of list of animal. And this might seem a little bit strange at first, and in most other languages, this would actually indicate that we're probably doing something wrong. Either we're not using that type parameter, or dog and animal are actually the same type, or some other strange corner case. In TypeScript, this actually has a pretty common use, and we're going to see exactly what makes bivariance in TypeScript. Right. Also assignability, since the type is bivariant and list of dog is a subtype of list of animal and the other way around, assignability can happen in both directions. So we have a list of dog is assignable to list of animal, and list of animal is assignable to list of dog. Right? We don't get errors on either one of those. And the final type of variance is, well, no variance at all, invariance. There's no arrow of inheritance between the two instantiations of list, right? This means that we cannot assign list of animal to list of dog or the other way around. There is simply no relationship between those two types. Okay, so we've seen a bit of theory. Now, the next question I think is fair to ask is, what gives a type parameter its variance? And I would like for us to try to form an intuition about variance, and to sort of be able to deduce on our own when something is covariant or contravariant or something else. And the basic question we have to ask ourselves when trying to figure this out is it safe? Right? Now, TypeScript is not always safe, and people who probably already know a little bit about variance are going to scream at their screens, because I'm going to oversimplify some things over the next couple of examples, but I promise we will add the complexity a bit later. But for now, let's start with the following supposition. The position in which a type parameter is used will have an impact on variance. And let's see some examples of how a type parameter can be used. So I have some sample code here. These are our sample classes, very basic. We have an animal base class, and dog and cat are subtypes of animal, each with their own method and fields. And we're going to start out with a simple example. Let's assume we have an interface that we're going to call cage that has a read-only field of type animal. And let's see if we can intuit what the variance of cage is. So the first thing we do here is we create a new dog cage. And let's see, can we assign a dog cage to an animal cage? Well, TypeScript seems to think this is fine. And let's analyze it a little bit. I mean, if we have cage and we access the animal field, we can only access weight. We can't access any of dog's methods, but that seems fine. That's generally how aliasing through a base type works. What you can do with the result is more restrictive. If we try to assign the animal, for example, if we try to assign a new cat here, well, the field is read-only, so we can't do the assignment. So this, again, seems safe. So there's nothing unsafe we can do if this assignment is allowed. So we can deduce here that this covariant assignment is allowed. So this field is this usage of T is covariant. Let's see if the other way, or if it is also contravariant. Now, if we have a variable of type cat cage, can we assign an animal? Cage to it? Well, TypeScript doesn't allow this. It doesn't think this is safe, and the reason for that is quite simple. I mean, here we've aliased our dog cage. So now in our animal cage there is a dog, but here we assigned it to a cat cage. So now we're going to tell our animal to play. Or treating our dog like a cat. So that's probably not going to work, and we're going to get a runtime error because of this. So field positions are not, read-only field positions are only covariant. Okay, that seems simple enough. Let's see another position we can use a type parameter in. What about as a return type? So here we have an interface with a method that returns an instance of its type parameter. And let's say we create a new object, and we return a new dog from our create method. Is covariant assignment safe? Can we assign a dog mother to an animal mother? Well, if we invoke the method, the actual implementation will be returning a dog. We can't access any of the dog methods since we aliased it through this base class field. We can only access weight, but again, that's fine. It's not unsafe. It's just we can do less. What about the other way around? Is that safe? Well, if we try to assign an animal mother to a cat mother, Typescript tells us this is not okay. And if we think about it, yes, it's not, because create will return something that we will think is a cat, and we will treat it as such. So we're treating again our dog. We're treating it as a cat. So not safe, right? So return types are covariant. What other positions could we use our parameter in? Well, another very obvious one is as a parameter type. So let's say we have a new interface. We'll call it groomer. It's an interface whose implementation will cut the hair of an animal. We create here a new dog groomer, and we first of all tell our dog to bark, and then we cut its hair. So let's see. Is it safe to assign a dog groomer to an animal groomer? Is it safe to assign covariantly? Well, Typescript doesn't think so. And if we try, for example, to invoke the method, since now the method accepts any animal, we could potentially pass in a cat here. So now the implementation, which is expecting a dog, is going to have to deal with a cat, and it's going to tell our cat to bark. And cats don't bark, and it's probably going to claw you if you try to make it bark. So definitely this is not safe. So parameter positions are not covariant, right? We cannot safely assign a dog groomer to an animal groomer. What about the other way around? If we create an animal groomer that can groom any animal, right? Let's say the cut hair method first of all weighs the animal, it prints out the weight, and then it proceeds to cut the hair. Is this safe? Well, if we assign our animal groomer to a cat groomer, what can we do here? Well, we can only invoke the cut hair method with a cat, but our implementation can deal with any animal. So this is safe. It's again more restrictive, which we would expect from an assignment to a base type, but it cannot result in a runtime error. So what we can deduce from this is that covariant assignment is not safe for parameter, but contravariant assignment is valid, is safe. So parameter types are contravariant. Now, as a general rule of thumb for variance, we can think of it like this. If it comes out of the implementation, such for example as the return time of a method or a read-only field, then it's going to be covariant. If it goes into the implementation, right, like the parameter type, the parameter, then it's going to be contravariant. And actually some languages codify this in syntax. For example, C# actually has an explicit covariance and contravariance annotations. For example, IEnumerable is a interface that produces elements of type T, so it's covariant and it's annotated with out. Or for example, function signature such as action is annotated with in, meaning for its parameter types, meaning that it's going to be contravariant. Now, TypeScript doesn't have an explicit annotation for variance. Its variance is determined by position, just as we've seen. And let's see if our intuition holds up with what TypeScript actually does in practice. So for fields, TypeScript, for read-only fields, TypeScript indeed considers those as covariant. Now, the problem is that it also considers mutable fields as covariant. What does this mean in practice? Well, consider our first example with our cage. we said that this is safe because we cannot assign the animal field because it's read-only. But if we remove the read-only modifier, then this assignment is still safe because mutable fields are covariant. However, we end up assigning an animal, we end up assigning a cat to what used to be a dog cage. So if we were to access, for example, dog cage, animal.bark, we are now telling our cat to bark. And again, probably not, the cat is not going to be very happy to do so. So mutable fields can be an issue. They're covariant even though that is not safe. Return types, TypeScript considers covariant, which is the same as our intuition said. And let's see parameter types. Now this is where it gets a little bit messy. As we've seen, parameter types seem to be contravariant, but only when strict function types is turned on and only within function signatures, right? Now, I'm not going to consider the case without function signatures. I hope everybody's using strict or some version of strict at least. But if strict function types is off, then parameter types are bivariant. And if you use strict, it doesn't mean you get away without knowing what bivariance is, because method signatures are always bivariant. So what does bivariance mean? Well, if, for example, we take our parameter example, right? Our groomer example. You will see here that I cheated a little bit. This isn't actually a method. It's a field that happens to be a function. If I wanted this to be a method, I should have written it like this. Remember, like I said, methods treat their parameters as bivariant always. This means that now we can assign our dog groomer to an animal groomer, as well as the other way around, which is safe. And now we can end up with our dog groomer being expected to groom a cat. So definitely we could get runtime issues from this code. So why is parameter variance such a mess, right? So we see that it's both unsafe and there's all sorts of weird options that you have to fiddle, and there's 3 cases. Well, initially, all parameters were bivariant. This was done from what I've been able to piece together because it's easier to migrate from JavaScript if this is true, right? Starting out with TypeScript, a lot of JavaScript developers didn't have to worry about assignability that much, so this was a good compromise for at the beginning. Now, in 2017, TypeScript added this strict function types option. And like I said, this option only affects parameter types in function signatures. And from the PR that introduces this is that it says that methods are excluded specifically to ensure generic classes and interfaces, such as array, continue to mostly relate covariantly. So what does this mean? What does Anders try to say here in this PR? What would happen if array were to actually, if all methods were to actually relate contravariantly, if method parameter types were to relate contravariantly? Let's have a look at how array behaves currently in TypeScript. So let's say we have a dog array, and we can take that dog array and assign it to an animals array, because array relates covariantly. Is this safe? Not really, because we can't now push in our animals array a new cat. But originally our dogs array, but we were just aliasing a dogs array. So for example, now if we were to process all of our dogs, one of them would actually be a cat. So in our dog array, we've mixed both cat and dogs, and I don't think they're going to be very happy to sit one next to the other. The other way around is not safe, but that's fine. That's the way it should be. So what would happen if method parameters were to be more strict? And I've taken the liberty here of creating an interface. I called it mutable array. And I've converted all of the method signatures to function signatures, just as we did for our groomer example. And let's see what happens. Now, since TypeScript uses this parameter both since we use this parameter both in a covariant position and a contravariant position, the result is going to be that our interface is going to be invariant. So what is invariance? Invariance is if we use a type parameter in both covariant and contravariant positions. This means that assignability between different instantiations of array becomes totally impossible, right? You cannot assign a dog's array to an animal array or the other way around. Is this safer? Yes, definitely. Is this developer friendly? Arguably not. Most people would expect this assignment to succeed, to be able to assign a dog's array to an animal's array. So could we build safer arrays? Could we build arrays that are strictly covariant or contravariant? Well, as we've seen, variance is determined by the position in which the type is used. So if we were to take each method of our mutable array interface, we could decide in which one of these two it should be. For example, the pop method. It returns something of the same of the t parameter type, right? Return type covariant. So this means it goes into our covariant interface. What about concat? Well, concat uses t both as a parameter type and as a return type. So concat is invariant as a method. It cannot appear in either of them. It would make the interfaces invariant as well. Push accepts a parameter of type t. This means it's going to go in the contravariant array bucket. Join doesn't use t at all, so it can easily go in both. And we have several other methods that are all covariant because the return type, the type parameters appears as the return type. Now, what about sort? Now, I said that if the type parameter appears as a parameter type, then it's contravariant. But here it's a bit more complicated. It's not directly in the parameter type. It's in a function signature that appears as a parameter type. Now we can fall back to our intuition, right? I said that if it goes into the implementation, it's contravariant. If it comes out of the implementation, it's covariant. Well, in this case, okay, we are passing a function to the sort method, and that does go into the array implementation. But then the array implementation itself calls our function with these two parameters. So we get access to something that comes out of our implementation, out of the array implementation. So this means that this appearance of the parameter t is actually covariant, right? Because we get access to it from the outside. It comes to us from the outside. We don't pass it in. We don't pass values of type t into the implementation. So this also goes into our covariant array bucket. Index of parameter, the type appears as the parameter to a method. So it definitely goes in the contravariant array bucket. Okay, now I get this, when I've explained this before, people tend to associate covariance with read-only and contravariance with write-only. That's not really what's the way we should think about it. In and out doesn't mean read-only and write-only. And as we see here, both interfaces contain write methods and read-only methods. Index of is definitely a read-only operation, but it's still contravariant. So have we actually succeeded? Are these methods, are these new interfaces covariant and contravariant? Well, for our covariant array, we see that, yes, indeed, we can assign the animal array to, the dog array to an animal array. And it's actually safe now. There's nothing we can do with our animals array that would result in us introducing a cat into the array, right? Pop it can change, but it can't add. It only removes. It removes animals from our array, and so do all of the other methods that are mutating methods. So it's safely covariant. Our covariant array is definitely not contravariant, which is great. What about our contravariant example, our contravariant array? Well, we can't assign our dog array to an animals array, which is what we expected. But if we were to have an animals array, we can assign it to a cats array. And here we can see that it is, we can use the push method to push in a new cat. But since the animals is supposed to be just an animals array and not something more specific, then this should be safe. Okay, now I'd like to talk a little bit more about how variance relates to types. So we all know that if we have types in TypeScript, all types have have a universal base type, and that's unknown, right? The base type of any type in the type system is unknown. It's a universal base type. Now there's also a universal subtype, and that's called never. Never is the subtype of any other type in the type system by definition. Now this also means that we can actually assign, if we have a variable of type never, we can assign it to any other type, right? So we can assign a variable of type never to a variable of type dog. And this is something that usually trips people up because never is seen more as an error type. It's not, it's just the subtype of everything else. Now, let's see how this relates to for example, our covariant array example. Now, let's see if we can express the base type of all covariant array instantiations. What would be the base type of that? Well, since the arrow of inheritance points in the same direction, the base type for covariant array of dog and covariant array of cat would be covariant array of unknown, right? This would be we can assign a covariant array of dog to a covariant array of unknown, and the same for cat. And what is the universal subtype? Well, that's going to be covariant array of never, right? So covariance respects the same relationships with regard to unknown and never. What about contravariant array? What would be the universal base type of that? Well, since we are dealing with contravariance, right? That means that, for example, if we thought that covariant array of unknown was the base type, that's actually not true, right? The arrow of inheritance points in the opposite direction. So that means that actually covariant array of unknown is the subtype of all covariant array instantiations. What is the base type? Well, that's actually going to be covariant array of never. So if we want to have a type that we can always assign a covariant array of dog or cat to, that's going to be covariant array of never. So for example, if we want to say have a function print that accepts the covariant, the contravariant array, if we were to use unknown here, we would see that we actually can't pass in a cat array, we can't actually pass in a dog array, we can't even pass in an animals array. We can't pass in anything because actually this is the subtype of all of these. If we were to pass in covariant array of never, then yes, this is the type which we can always assign another contravariant array to. Okay, so does TypeScript actually care about variance? I mean, it's obviously an emergent property in the type system, right? It definitely has impact. But does TypeScript actually use this in any way? Well, there's two ways that TypeScript definitely uses this. First of all is the error messages. If we were to look at our covariant and contravariant array examples, we would see, let's actually first of all look at our invariant arrays. Let's see what kind of errors we get here, right? It's one of those wonderful error pyramids, and it actually ends up reporting an error on a random method. Here it's concat because in order that was the one that ended up being the first one not to be assignable. But for example, for cat, it actually pop, that is the first one that is not compatible, and an error is reported on this. It's not a particularly great way to express errors. For covariant array, we see that the error message is much nicer. We actually see that, okay, we get the top line error, and then it says directly that animal is not assignable to cat. Since this is what TypeScript has deduced, that must happen, right? If covariant array is covariant, then for the arrays to be assignable, then animal would have to be assignable to cat. So much nicer error messages. What about for contravariant? Now here we see that we have the same assignability error. We have that dog is not assignable to contravariant array of dog is not assignable to contravariant array of animal. But then we see that here the assignability error is reversed, right? It says that animal is not assignable to dog. And this is quite commonly something that trips people up when they see this error. They think that it might be a compiler bug. No, it's actually just an expression of variance, because for the first assignment, for this assignment to succeed, it's not that dog has to be assignable to animal, it's the other way around. Animal has to be assignable to dog. So this is why we get the types reversed in the error messages. And TypeScript also uses covariance as an optimization to structural type checking. Structural type checking is very expensive, right? Checking all properties is not trivial for an instantiation of a generic type. But generally, if TypeScript can know that the specific variance of a type, and that's not always possible, it can sort of short circuit this. It can just say, okay, if I have this this generic type and I know its variance, I can just relate the type parameters. I don't have to go through all the whole type structural type checking thing. Now this can go sometimes wrong, and I've actually reported recently a bug that is specifically about this. If you search for it, you'll see it's very interesting in my opinion. But generally, this is something that TypeScript does, and if you build a strictly covariant or contravariant type, it will actually be faster in checking that. So I know what you're probably thinking right about now is, okay, but I don't use generics that much. Does this really matter? The answer is yes, because even though we've talked about variance mostly in terms of generic types, actually variance applies to all type relationships. So the positions that we've discovered that govern how variance looks like in TypeScript actually apply when TypeScript tries to relate all types. What do I mean by this? So for example, let's say we have an interface. It's a state machine. It has a function that's called setState that accepts two states, started and stopped. Now we also have a function that accepts an object that has a method that accepts one of these three states: started, stopped, and paused, and invokes this method with paused. And now we create a new state machine. And let's see, if we were to call move to paused state on our new state machine that only accepts started and stopped as a state, does TypeScript complain? Nope. TypeScript allows this. Why? Because methods relate bivariantly. Method parameter types relate bivariantly. So this means that as long as there is a relationship between this parameter and this parameter type, it doesn't matter what that relationship is. It can go in either direction. TypeScript will still be happy. Now, if there's no overlap between the two, then yes, we would get an error. But as long as there is some sort of relationship, TypeScript is happy. Can we fix this? Well, if we were to use a function signature instead, then yes, TypeScript does complain. So this is a place where the fact that method parameter types relate bivariantly results in something that could be a runtime error. Let's look at a similar example. Let's say we have our state machine, and this time we have a field. The field is not read-only, right? And our move to state to pause state method function accepts again a field that has a state that is similar, but it also accepts paused. Now, since function fields relate covariantly, this means that we can actually assign our state machine to this move to pause state function. And this is actually a harder issue to solve because mutable fields always relate covariantly. There is actually no switch to turn this off, unfortunately. And actually, the only thing we can do is to actually make this this read-only, and then we actually would get an error when we try to assign it. But this is something that we, as the implementer of the function, need to take care of, right? So there are definitely issues that you will have, and places where you will fall off the safety of that TypeScript provides. And a lot of these times, variance is at the root cause, and the way TypeScript deals with variance is at the root cause of it. So some conclusions. Yes, I still actually like TypeScript. I know I've been sort of pointing out some of its flaws, but I think that's also important. We have to know what the limits of type safety is in TypeScript and know where we're about to fall off the edge with something. This may improve in the future. Who knows? Maybe in 2 years, most of this talk is going to be obsolete. I hope so. But for now, here are some recommendations to make sure that you don't fall off the edge with regard to type safety. First recommendation would be prefer read-only fields, right? We saw that read-only fields relate covariantly, and that is safe. Mutable fields relate covariantly, and that is not safe. Prefer function signatures to methods. We saw that method signatures are always bivariant, while function signatures do actually respect variance more closely. And think about variance in your when you build interfaces. Try to make them either co or contravariant. And if that's not possible, at least make it invariant. If they can't relate, that is still safe, although it might be a pain for your users. Also, avoid making bivariant interfaces, because since assignability can go in either direction, usually that is a recipe for runtime errors. That being said, thank you very much for listening. If you guys have any questions, I'd be more than happy to answer them. Also, if you'd like to read more about TypeScript adoption at Bloomberg, there's a very nice article from one of my colleagues, which I encourage you to go off and read. Thank you very much.
Thank you, Tizian. That was quite insightful. And I think there's a lot to unpack there, certainly for me. So I think this is a great moment to take questions. So if you do have any questions, feel free to drop them in the chat. And okay, so we have the first question from Orta Therox. Hello, Orta. Do you prefer contravariance or metal slug variance?
I actually have not heard of metal slug variance, but that's a much cooler name.
So Orta, please do share more information. We want to know. John Riley is asking, he's saying awesome talk. Couldn't agree any more. Is there a good way to reference to turn to when making your code more variant?
I don't know of one. I'm sorry. I most of the things I present here are sort of some of this personal experience and things I've noticed. So it's sort of fresh material, but I think that everybody can think about this. You know, once you sort of have the vocabulary for it, you can start thinking about it.
Mm-hmm. Okay, and we had so John Riley just said, "Will you write it?"
I have a sort of very long list of blog posts I would like to write. I haven't written any of them, so I'm not particularly hopeful that I will get around to doing that. But that's actually a very interesting topic that I might actually manage to put pen and paper to.
Do you mind sharing maybe 2 other topics that you would love to address in one of your blog posts?
Actually, none come to mind right now. Let me see. I think conditional types, and again, distributive conditional types is something that people are always tripped up by. And I might be late to the party here, but I think the new support for string literal type manipulation in TypeScript is also awesome. But I'm pretty sure that a lot of other people have covered that as well. So I'm not sure if I would have any more insight to bring to that. So.
Yeah, I believe we had a great talk from one of the Spotify engineers at one of the previous meetups exactly about string literals, string literal types. Okay, we had another question from Jakub, who asked, how does it work in other languages like PureScript? Are you familiar with PureScript?
I'm not familiar with PureScript, so I can't comment on that. I'm so the language I'm most comfortable with is C#, other than TypeScript. So in C#, there's most things are actually invariant, and for classes you can specify that interfaces are co or contra variant, and you have those explicit annotations. But it's definitely more strict than TypeScript is.
I see. And were you using C# prior to TypeScript, or were you sort of learning both in parallel?
Oh, there was a good time. There was a good period where I used both. I think it's quite a long time. I don't know, 4 or 5 years. I used them in parallel. I think for the past 3 or 4 years I've been exclusively in TypeScript.
Mm-hmm. And one final question, Diego is asking, do you miss explicit variance keywords?
Well, in TypeScript, the only thing that would happen is that you would get errors if you weren't respecting those, because the position determines it anyway. I don't know. I don't miss it, because actually in C# it's not common to use them, mostly because people don't expect assignability to be so easy there. There's lots of time where things just aren't assignable and everybody's fine with that. I think coming from JavaScript is sort of there's more demand there for things to just work, and that is, I think, why the rules around variance are more relaxed in TypeScript than they are in C#, for example.
I see. Gotcha.